So, let us start this lecture with a thought process that question can never be silly, it can be a beautiful lily in the garden of knowledge, that is the truth age after age. In the last lecture, we basically looked at the laminar premix flame, and by discussing about the Bunsen burner and how the mixing takes place and how the flame is stabilized, right. And today we will be dabbling with the same premix flame. Let us look at a LPG air Bunsen flame photograph, which looks to be a very sharp image here. And if you consider this flame, right, is it the whole flame is what that let us look at it. See, is it the entire this thing as a flame? You consider, if you take this is image, that if I take a cross section of this, right, if I take a cross section of this, right, what will be the flame shape? Will it be entire like this? It is, this will be my flame, this won't be my flame, right. My flame would be, this portion will be my flame, right. The other portion is hollow, there won't be anything, you know. That means in the thin region this is not a flame. I am talking about this cross section, right. So, therefore, flame is a very, flame occurs in a very thin region in which the rapid exothermic reaction takes place. So, if you look at in this thin region, right, the rapid exothermic reaction takes place, and what we call it as a flame. Are you getting point? So, this you can call it basically dark zone, this hollow region, and this is of course the light zone, right, that you should keep in mind. And of course, in this figure it is taken in such a that this is the very, this region is the flame, which is very, very sharp, but whereas the blue color is here, right. And question might be arises, you know, why this blue color coming in the center also, this portion, why? Because you are taking image from the front. So, therefore, the flame is there also, right, because you cannot avoid it. So, that is coming, whereas if you take these edges, that is basically the flame. Flame is this annular region, this annular region is the flame, the inside nothing will be there. So, the luminous zone we call the light zone or the luminous zone, right. The portion of the flame in which temperature is high has several radicals to emit radiation. Why it is? Because temperature in this case will be very high temperature, this will be high temperature, right, zone. So, there will be several radicals which will be emitting the light, and that we could see. See, if you look at, you could see a blue color flame. Now, why blue color? You can also see a flame which is yellow color in nature. You can see sometimes purple color flame, right. That depends on the basically the radiation emitted by predominant radicals, right. And flame radiation, it will be something 3000 to 700 angstrom kind of things. And however, you know, there will be some color which will be predominant, some zone, and that does not mean that there will not be other color, but those are not those are being masked by that. If you use a spectrometer, you will find various, you know, spectrums corresponding to the particular radiation band, it will be there. So, where the chemical reaction takes place is basically below this luminous zone. This is luminous zone, like and just below that there will be chemical. So, if you look at this, if I say this chemical reaction will be taking place here below this, this is the chemical reaction zone. And keep in mind is not that it will be only happening here. As we proceed, we will see that the reaction will be occurring a little thicker zone, but however, the predominant reactions where the heat release will be occurring will be in a narrow zone. And what will happen above reaction luminous zone? That is basically the burned gases are cooled and diluted by the ambient air, because if it is a hot gas, right, and if it is because of buoyancy and also some momentum will be there, but buoyancy will be there at this thing, some air will be entraining into this, because it is open flame. So, this will be air entrainment will be occurring. So, from the ambient, and there will be getting cooled down the gases, hot gases, and they diluted by the ambient air, right, in the above this. So, the region where unburned gases are heated to the critical temperature in this region, right, if you look at this is my flame, let us say this is fuel plus air mixtures and this is my flame. So, in this is known as the dark zone. In this case, what is happening, that the unburned mixtures are coming, right, fuel air, that is getting heated, right, because of presence of flame, and flame will be giving the heat, right, due to conduction and what you call convection, and also the radiation will be more predominant, right, in this case. So, therefore, that will be preparing the mixture to attain the certain critical temperature, so that ignition can take place, and that makes the flame to be self sustained, even though you initiate the flame or combustion with the ignition energy, but afterwards you just stop this providing ignition, still it is being maintained. That means, this process makes the flame or the combustion to be self sustained, and this dark zone plays a very important role. So, which is the zone of highest temperature in the flame? Generally the luminous zone, or the just below where the reaction will be very predominant, the temperature will be very high, right. The color of luminous zone depends on the type of fuel air or fuel oxidizer, rather I would put it as a oxidizer, right, because right air is one of the oxidizer, and its ratio means is equivalence ratio, which will be basically, or the fuel air ratio, which will be dictating the color of the flame. The lean flame, generally it will be blue in color. This is the lean flame. Lean means fuel lean mixture, right, that we call it as a lean flame. So, blue color due to what? Because there will be OH radical which will be more predominant, and that will be giving the radiation in the this thing. So, that is why it is the blue in color. And when you will decrease the mass flow rate of air, right, per a fixed fuel flow rate, what will happen? This will be basically the fuel reach, because air mass flow rate you are changing. That means, it is, if it is a stoichiometric, and then you are decreasing the air mass flow rate, what will happen? Naturally it will be fuel reach, and if it is fuel rich, you will get in yellow color flame, right, like this you will get. This is a rich flame, right, and that is due to the excitation of C2 star molecules, right. This will be. So, having said this thing, what we will be interested to look at is basically look at the structure of a one dimensional flame. See, flame looks to be very simple when you look at a photograph, but what is happening inside we need to look at it. And the flame zones, as I told, it can be broadly divided into 3 zones. One is preheat zone, other is reaction zone, other is the recombination zone, right. The flame zone where the flame is occurring is divided into 3 zones. So, from the, if you look at the one dimensional we are considering, but in the case of Bunsen burner, flame is not really one dimensional, it is a 2 dimensional, you can say, if you consider the it is symmetric along with the theta direction azimuthally. So, therefore, it is 2, but if I consider the one dimensional, right, I will get a structure like this. And if you look at, this is basically temperature profile, the TU, this is unburnt temperature, and it remains same, almost constant, but however it started slowly increasing and then it goes to a peak temperature. And although I have made it flat, but in some case of particularly hydrocarbon, this goes on asymptotically increases. This is only for the hydrocarbon air flame, but not for others. But however, this is asymptotically increases for hydrocarbon, this is for hydrocarbon air flame. But for our purposes, we will be considering that it is just flat, that is, this is basically Tf, this is the flame temperature, and if I consider this as a adiabatic, then that is equal to adiabatic temperature, but right. So, it will be approx or rather adiabatic temperature, considering that there is no heat loss from the flame, but in real situation there will be heat losses. So, there will be lower temperature than the adiabatic temperature. Okay. Now, what is happening, if you look at reactants, this reactant is fuel plus oxidizer, it can be air, it can be any other things, right. Both the profile will be similar, okay, it not same. That means one can be fuel profile, other can be oxidizer profile, right. Rather I would suggest that profile will be similar, right. I can say this is a basically fuel, right, and it will be goes on and then it decreases and it remains almost 0, it is 0 at the recombination zone, and the heat release is occurring here in this region, and there will be intermediate reactions which will be occurring in these regions. Keep in mind that this is the zone which is very important, this is known as reaction zone, and this reaction zone will be heating up this preheat zone, therefore, we call it as a preheat zone. And recombination, where there might be some of the products which will be going on, like going on, and then it is. So, if you look at this is you can broadly divide into 4 zones, like preheat zone, reaction zone, recombination. Some heat being released here also in actual situation, but for our analysis case we will be talking about only 3 zones, okay, keep in mind that. And there will be a zone where there won't be any rise in the temperature. So, if you look at the human life also divided into 4 regions or the zones, you can say the human particularly according to our Indian what you call scriptures, the life is divided into 4 parts. One is the brahmacharya, other is the grahastha and other one is Banapastha and Sannyas. So, it is similar to that. That means, in the Brahmacharya what you do, you depend on the society, or your father mother will be empowering you to contribute. That means, you will be preheating zone, right, the preheating zone corresponding to your Brahmacharya. You are not earning anything, you are not contributing anything, you are just taking and then empowering yourself. Then afterwards, in the reaction zone, that is the Grahastha zone, where you will have to use your energy and a lot of things you will be doing, contributing. And in the Banapastha zone, you will be little slowed down and you will be still activities will be going on, but you will be not really very much productive or something. But in the Sannyas zone, you will say, look, good enough, I will only talk about the God and other things. Okay. So, beautifully the Indian way of life being defined, and it is the similar to the flame. Are you getting? Are you getting my point? This is a very important point I am saying. So, therefore, we need to follow those reasons to contribute for the society, not for ourselves. So also the flame. Flame is always the fuel oxidizer get burnt and give the heat to the others, right. So, preheat zone, if you look at, there is an interesting thing that negligibly heat release, there will be some heat release, heat release. If you look at, consider here this portion, right, this heat release is, this is basically heat release, right, is approximately equal to 0 as compared to the heat release this portion. This is very high, large amount. So, if you look at this region, if I consider these are the region where heat will be released, it will be very high, and it is occurring in a very thin region. Keep in mind that this I have exaggerated, this portion if you look at, I have exaggerated, this is the reaction zone, but in real situation it will be order of maybe less than 1 mm, right, and this will be much larger, but I have exaggerated just to make the point clear to you. So, the reaction zone, in this case what is happening, like in the preheat zone certain chemical reaction actually take place in this zone. It can be several reactions, certain things which is initial phase, but however the heat release will be very, very small, and most of the things like pyrolysis and other things occurs in this zone. That means, and some maybe exothermic reaction will be taking place in this region, but generally the fuel get pyrolyzed. Pyrolyzed means endothermic reactions, right, some heat will be coming and the hydrocarbon, higher hydrocarbon converted into the lower hydrocarbons and other molecules which can be consumed. And the reaction zone, most of the chemical energy is released in the form of heat in this due to the chemical reactions. Keep in mind that several reactions will be occurring, as I had told earlier, that for a methane systems, which is a very simple hydrocarbon, where something order of 100 reactions takes place, right. Are you getting? It's in this thin region there will be some 100 reactions will be taking place, right, involving maybe 20 species, right, and which is quite complex in nature. And decomposition of fuel takes place, leading to intermediate radicals formations will be taking place, and reactions are very thin as compared to preheat zone. I have already talked about it. And temperature gradient, see, if you look at, gradient is very high here in this reaction zone, and so also the concentration gradient, right, this basically reactant is the concentration gradient will be very high. So, recombination zone and carbon dioxide and water are formed, particularly in the recombination zone, and of course, later on there will not be much things will be taking place, rather the heat losses will be more at the recombination zone and other zones. So, and negligible or the zero heat release occurs in this recombination zone, right. There will be a little bit, but that is negligible as compared to the reaction zone. So, when you talk about, we talk about basically comparatively, right. Now, we will be trying to analyze this laminar flame, right, considering the thermal theory, and there are several theories are there, and this is basically we will be considering the simpler one and we will be making certain assumptions, right. Before making some assumption, let us look at, this is my let us say fuel air mixture. Filled in this tube and we are just igniting it. Right, what will happen? There will be flame kernel will be taking place and it will be taking a shape and then it will be moving, right, moving towards the unburnt, this is unburnt fuel air mixture with a certain velocity, that we call it as a burning velocity SL. The SL is the movement of the combustion wave, this is a combustion wave. What we call it is a flame in in current situation, and this will be moving with respect to unburnt mixtures, and this velocity is defined as a speed with which combustion wave will be moving with respect to unburnt mixtures, right. Now, this is a propagation of the flame, but as I told earlier, what we will do, we will supply this fuel air unburnt mixture, right, fuel plus air or fuel or oxidizer, I need not to confine to air only, oxidizer mixture with certain velocity such that it will be equal to the SL, so that my flame will be stabilized here somewhere, right. So, if I look at, that means my flame, I am considering this as a one dimensional flame, 1D flame, right, and keep in mind that fuel air is supplying, fuel plus air is supplying at certain velocity which is equal to the SL. So, that my this is fixed. So, I am considering this as my x in the fixed coordinate system. Now, the flame is fixed, is not moving, because I am putting this reference frame with the flame, right, basically we can put that way, and then it is fixed. So, with this and then this side, what I will be considering is a far away, it is infinity and this is minus infinity, right, are you getting, and this is we are considering one dimensional flame. So, with this what we will be doing, we will be making some assumptions. So, assumptions are, we are considering one dimensional steady inviscid laminar flow. The flow is laminar and it is steady, there is no viscous effect, right, hypothetically we are considering, but I can have established a flame which is just lifted one dimensional flame, like which is stabilized in a burner. I will see, I will show you a burner, one dimensional burner, by which you can really establish that in the lab. I had done that maybe 25 years back myself. So, of course, it is quite difficult to design that and develop. So, flame is quite thin, right, that we are considering, and the ignition temperature is close to the flame temperature. That means, in this case what we are considering, T ignition is approximately equal to Tf, or very close, there is not much difference, you can say, and the no heat loss including radiation, but in actual flame radiation you cannot avoid because flame temperature is very high, and ideal gas law can be valid, and single step chemistry model will be using. As I told, in the flame there will be several reactions will be taking place, involving several kinds of species, even for simple hydrocarbon for methane air. Binary diffusion and Fourier's and Fick's laws are valid. We are considering binary diffusions because fuel and oxidizer only, right. And the unity Lewis number we will be using it. So, constant transport properties we are considering, we will be considering constant properties, and with these are the assumption we will be considering, but with this we will stop over and we will discuss in the next lecture and also trying to derive a relationship for burning velocity in the next lecture. Thank you very much.